With aldehydes and ketones, I do want to talk about one other reaction that they do undergo, and that's an aldehyde or a ketone, and that is a reaction of either one of those guys with an alcohol, plus an alcohol, and maybe two alcohols, and what happens in those cases. So the first thing that's going to happen if we take an aldehyde, take any aldehyde we like. Let's do a nice small one, maybe. There we go. That's not too bad. And if we add an alcohol to it, and it doesn't really matter, how big the alcohol is. So we're just going to add methanol here. So we have our aldehyde, and we have our alcohol in this case. And what's going to happen in this case is the alcohol is going to add basically in two parts. So this alcohol is going to add in as this oxygen carbon group, and it will then also add in separately as a hydrogen. And from our conversation, you could probably imagine where it's going to go. If you had to take a guess, where is these guys going to go? They're going to go right here where our carbon oxygen double bond is. At this point, though, there is not enough room to add both of these guys in. So this guy is going to add in, like everything else that we add into like a double bond. One goes to one spot, one goes to the other spot. But we do have to basically make that double bond into a single bond. So what's going to happen is, much like all of our double bonded things that we're going to add in, we're going to redraw this exactly the same way, except that we're going to remove the double bond and make it a single bond. And that's going to allow space for everybody to come in. So again, it's very much like our alkene, where we add something to it that we're just going to make it into a single bond. So it's basically the same idea. Now, in this case, what we are going to add is the alcohol. The alcohol is going to be added just like everything else. The hydrogen will come in. I'll make it blue. The hydrogen will actually come in to here. That's because really the oxygen here is more negative, and this hydrogen is really more positive, right? And if you think about this OH bond in the alcohol, right? The OH bond is a polar bond, right? The hydrogen is more positive, the oxygen is more negative, and the carbon here is actually more positive. So what ends up happening is the hydrogen will end up on the oxygen because there's the opposite attraction that occurs. And what that leaves is this oxygen carbon group that really is more negative, and it's going to be attracted to the positive carbon, and it will end up exactly the way it is, just like this. So in blue is really our alcohol that the H went to the oxygen, and that always happens. The H will go to the oxygen, and I call it like an oxygen carbon group. So there's always like an oxygen with the carbon that's left over, and that will go to the carbon. And what we made here actually has a special name. It is what is referred to as a hemiacetal. So this thing right here is what is referred to as a hemiacetal. There's some important parts that actually make a hemiacetal. In order to be a hemiacetal, you pretty much need these things, and I'll highlight them. You need an OH, which by the way is like the hemi part of it. You need an oxygen carbon group attached to a carbon, and you need a hydrogen. And that's because it comes from an aldehyde, so it's a hemiacetal. And that's what happens when you add one alcohol to an aldehyde. Any questions on that there? Now, what's going to happen next is this hemiacetal actually can take on one more alcohol. So you could add one more alcohol to this. So I'm just going to redraw my product here so we can see what happens. So we have this guy. And we're going to add another alcohol. Could be the same alcohol, could be a different alcohol, but we'll use the same one here. And the same thing's going to happen in this case. In terms of the alcohol is going to add as an H and an oxygen carbon group. But the difference is here, we don't have a double bond or anything like that to make room for it. So what's going to actually happen is we're going to actually make water in this case. And the water is going to come from the OH that's here and the H from the alcohol. So those guys are going to come together basically to make water. We'll highlight it over here. So that will make water. And what happens is this entire thing will be exactly the same, except obviously we'll take the OH off. And when we do that, we will have our CH3, CH2, our CH, our OCH3. And now there's kind of like a hole there at the carbon right on top. And what fills it is this guy. This guy then comes in and basically takes that spot. And we add an additional oxygen carbon group. I'll make it blue up on top. We add this guy in. And this guy also has a special sort of name. This is what is known as a acetal. And what makes something an acetal is there is two oxygen carbon groups and a hydrogen attached to a carbon, basically the same carbon. So attached to the same carbon, there's two of these oxygen carbon groups which come from alcohols, and there's a hydrogen attached. So if you take an aldehyde and you add one alcohol to it, you will make what is known as a hemiacetal. You can think of it as the hemi should have an OH story association with it. And if you add a second alcohol to that, it will go all the way to what is known as a acetal. Any questions on that? Now, this exact same reaction happens with ketones, and it basically works the exact same way, except that it's sometimes called a couple different things because you started with a ketone rather than an aldehyde. So let's take a look at what happens if we do really the exact same reaction with a ketone. If we take a ketone, and we'll just do a nice simple ketone here of this guy. So if we take a ketone and we add an alcohol, we'll do a little bigger alcohol this time. So once again, pretty much everything here on the ketone is going to happen at that carbon-oxygen double bond. And exactly the same thing is going to happen with our alcohol. We're going to add an H, and we're going to add this oxygen carbon group. Again, the H is more positive, the oxygen is more negative, oxygen is more negative, and the carbon is more positive. So just like before, we're going to make room by making our double bond into a single bond. So that's a good way to do it. Just draw it exactly the same. Make our double bond into a single bond. And just like before, our hydrogen, which is more positive, will end up at the negative oxygen. Our negative oxygen here will end up at the positive carbon. Again, opposites attract. I'll put them in as red. So we'll get a hydrogen here, and we'll get that oxygen carbon group attached here. So it's basically identical to what happens with an aldehyde. The difference is some people will actually call this as well still a hemiacetal. So some people will still call it the exact same thing, but other people will call it a hemiketal. And that's because it starts from a ketone. So sometimes people call this a hemiketal, but I will say some books, and maybe your author as well, they will sometimes call it a hemiacetal as well. So, but some people will call it hemiketal. And the same thing's going to happen. We could then add another alcohol to it. So if we take our hemiketal that we just made, and before we do that, by the way, a hemiketal has a couple important characteristics. It has, again, the OH group. It has the oxygen carbon group, but different than the hemiacetal is on this carbon, there's no hydrogen. So there's no hydrogen on this guy. That's different than what we see here, where there is a hydrogen on the aldehyde. That hydrogen stays from here. But because the ketone didn't have a hydrogen to start with, it doesn't have a hydrogen there on the hemiketal. So that's a key difference. If we take this hemiketal and add one more alcohol to it, once again, it's going to add the same way with our hydrogen and our oxygen carbon group. And once again, it is going to be the OH and this H here that's going to come together to make water. And once we do that, pretty much everything else here will stay the same. So we'll redraw it exactly the same. And once again, we can see the top there is sort of missing something. And what is missing is this guy that's left over. So we'll put the other oxygen carbon group up on top, and we'll get this OCH2CH3. This is what is sometimes referred to as a ketal. Important part of a ketal is, much like an acetal, it has two oxygen carbon groups, and once again, no hydrogen on the center there because it started from a ketone. That's how you could tell that this guy started from a ketone. It is missing that hydrogen on the center carbon there. And if you do see the hydrogen, like in the previous slide, then you know you started with an aldehyde. So these are two reactions that both aldehydes and ketones could have if you put in alcohol. So once again, if you kind of put just one alcohol, you'll end up with either a hemiacetal or a hemiketal, which has the OH group. And if you put two alcohols, it'll go all the way to the end where there is no OH groups, but there will be two of those oxygen carbon containing groups. Any questions on that? We sometimes will see hemiacetals and stuff like that when we talk a little bit about carbohydrates in that chapter. So sugars can kind of open up and close and make some of these hemiacetals. Any questions on either of those reactions there? Okay, so I did want to go over that there. So what we'll talk about now, I think, is we'll do a little preview here of, we got a little bit into carboxylic acids earlier. We'll talk about esters as well. So let's take a look at these guys here. Do some. Okay, so carboxylic acids, as we saw when we oxidized our aldehyde, have the functional group of carbon oxygen double bond to the OH. And once again, as I mentioned earlier, because of that hydrogen there at the end, it has to be at the end of this group. So it's very similar to an aldehyde in that sense. As I mentioned earlier, it has to be at the end. And you do not need to give the location of that carbon oxygen double bond. This is a very polar group. Both the carbon and the oxygen here are polar. Plus you got the OH group that's also polar. This is the one thing that actually can beat out an alcohol in terms of boiling points and melting points, because it could actually double hydrogen bond with itself. So you have both of those spots at the carbon oxygen and the OH group. When a couple of carboxylic acids get together, there is a lot of interaction that can happen between these two different groups. So the negative, the positive, the negative, the positive. So we could have some hydrogen bonding happening there. We could have some hydrogen bonding happening there. So there's a lot of hydrogen bonding that could actually happen when carboxylic acids bond with themselves. And because hydrogen bonding is a really strong intermolecular force, they have very high boiling points. So up until this point, really the alcohol is sort of the largest in terms of boiling points because it could hydrogen bond, but because this guy could do a lot of hydrogen bonding within itself and make a lot of dimers by hydrogen bonding with itself, it has a much higher boiling point. So it's one of the few things that can really sort of beat it out. Also, it should also be fairly soluble in water because of all that hydrogen bonding that can take place. But like most organic things that we talked about earlier, you will start to see sort of a decrease in solubility, as you kind of build out the carbons and hydrogens, but it will be pretty soluble in water. So we talked about sort of naming, and again, these guys are named using OIC acid as a replacement to sort of the longest carbon chain. So you do want to look for the longest carbon chain that obviously has that group in it. So if we had something like this. All right, I don't know what I drew, so let's throw some hydrogens. Let's see what I came up with there. All right, we'll do that. We'll throw a hydrogen there, throw a hydrogen there, throw a hydrogen there, there, and there. All right, so let's see what we did here. We're looking for obviously the longest continuous carbon chain, right? That contains the functional group, which is over here. So that is going to be, if we go this way, 1, 2, 3, 4, 5, and 6. We could also go 1, 2, 3, 4, 5, and 6 that way. So it looks like it's a tie no matter which way I go. So it does look like 6 is the longest continuous carbon chain, either going straight or going straight then down. So we'll get rid of that one and we'll go that way. So going straight is going to give us 6. 1, 2, 3, 4, 5, 6. 6 is based off of hexane. So we're going to drop the E and this will become hexanoic acid. Once again, because this group has to be at the end, we do not need to give a number like 1 hexanoic acid or anything like that. But in terms of numbering, as we talked about, it does need to be number 1. So that is number 1. That means that is number 2. That is number 3. That would be number 4. That would be number 5 and number 6. So we can see at carbon number 3, we have a chloral group. At carbon number 4, we have a 2-carbon group, which is a ethyl group. And like normal, we will put these guys in alphabetical order. So we're going to go with chloral first here. So this would be 3-chloral, 4-ethyl hexanoic acid. That is a mouthful. Yes. Any questions on that one there? All right, so I did one. Why don't you do some? Let me think here. Do a little line structure. I feel like I haven't drawn one yet today. We'll do a randomly put lines. Let's go. I have no idea. I'm just drawing lines. All right. Let's try that one. Let's do that one. And let's do this guy. And then let's draw or bromoheptanoic acid. I try to decipher what I drew on top there and see, hopefully I do something correct. So first off, my crazy line one here, hopefully you can recognize it as a carboxylic acid. That is the carboxylic acid group there. That's the carbon oxygen double bond with the OH. We then want to count, obviously, the longest carbon chain that has that going on there. So that is 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, 8 carbons. All right. Then we also possibly could have went 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, 8 carbons, which gives us the same. So we might as well just take the straighter one there. It doesn't really matter. You could go either way. So we'll redo it here. We'll just go with the straightest. So our straightest, longest carbon chain going to be basically 1, 2, 3, 4, 5, 6, 7, 8 carbons. 8 carbons is based off of octane, and since it does have the carboxylic acid group, this would then become octanoic acid. Once again, where the carbon oxygen double bond would be is carbon number 1, which means this would be carbon number 2. That would be carbon number 3, where we have a methyl group, right? Carbon number 4, carbon number 5, where we have really a 1, 2, and I guess 3 carbon group there, which would be a propyl group. And that's all of our groupage. So we're going to go alphabetical on this. So we will go methyl first. So try to squeeze it in here. 3-methyl dash 5-propyl octanoic acid. Yeah. Also a mouthful on that one. Yeah. So I guess I did draw something rather than just lines. I guess it worked out. Yeah. Any questions on that one there? All right. We'll go to the right there. Also, that right there is our carboxylic acid group. In this case, we could just go straight across. So that is 1, 2, 3, and 4 carbons. So that's going to give us butanoic acid as the base of our name. Once again, this is going to be carbon number 1. That makes that carbon number 2, where we have a bromol group. And at carbon number 3, we have a chloral group. So putting that together here alphabetically, we will go with 2 bromol, 3 chloral, butanoic acid. Butanoic acid. Any question on that one there? How about this guy? That is a what type of ring? It's a benzene ring, right? It's got the 3 double bonds in there, or a circle. That is not, again, cyclohexane. That is not cyclohexene. Again, the circle R is equivalent where they do just draw the double bonds in, again, is benzene. This also is the carboxylic acid group attached to it. So this is the same deal. We just dropped the last part there. This becomes benzoic acid. I'll spit that out, I think. So that's benzoic acid. You can see here, much like the aldehyde group in this ring, it is not incorporated into the ring because of that hydrogen. So just like the aldehyde, it cannot get into the ring part of it. So what that means, though, if we did have another group attached, say we threw a methyl group there, this guy where that carboxylic acid group is located would be carbon number 1. And then obviously you would go whichever way gets you the smaller number. In this case, you would go to the right and it would be 2-methyl benzoic acid. So much like the aldehyde group, they kind of end up being sort of an appendage off of the ring. because of that hydrogen, they can't incorporate themselves in there. So whichever carbon they're sort of attached to in the ring will be carbon number 1 for numbering purposes. You still don't need to give the like a 1 for the location of it, because again, wherever it is on the ring, that carbon will be carbon number 1. Any questions on that there? Okay, so going backwards here, I see an acid and I see heptanoic acid. So the oic acid should tell me I got me a carboxylic acid group happening. And heptanoic acid means heptane, which is 7. So we're going to lay up our 7 carbons. I think that's 7. 1, 2, 3, 4, 5, 6, 7. And much like the aldehyde group, you could throw this group on the left-hand side, right-hand side. It doesn't matter since you're drawing it. I'll go to the right here. I do want to use this carbon as part of the group. I don't want to add in another carbon. Otherwise, I'll end up with 8 carbons, right? Which would be too many in this case. Once again, that's going to be carbon number 1. And that will take care of basically all that. That means that carbon number 4, I have a bromine, which would mean that's 2, that's 3, and right here is 4. And everything else like normal will just be our hydrogens. So this will be 2, this will be 2, that will be 1, that will be 2, 2, and 3 there. And again, if you did a little line structure action, look, you know, something like this. We got there 1, 2, 3, 4, 5, 6, 7. Out to an OH and a double bond. That'd be 1, 2, 3, and 4. Something like that. If I get out of the way, it would look something like that. Yeah. Any questions on carboxylic acids, how to name them, how to draw them? And as we talked about earlier, we get a carboxylic acid from the oxidation of an aldehyde, right? So that is the product that we get from the oxidation of an aldehyde. And again, if we go backwards, we get our aldehyde from the oxidation of the alcohol, right? So that's the pathway to making these guys. Now, this guy here, the carboxylic acid, is actually very important in terms of making another organic compound, which are known as esters. So an ester has the functional group of carbon oxygen double bond to an oxygen to a carbon. So it is based off of really a carboxylic acid, and it has that as the functional group. The difference is there's no H at the end. So unlike the carboxylic acid, this functional group will always be away from the end. Yeah, so it'll always be, you know, kind of away from the end. You won't have the carbon oxygen double bond at the end. It'll be in usually at least 1 carbon in most cases. So how do you make it? You make it through a wonderful reaction known as an esterification reaction, which you will be doing next week. You'll be putting things together and huffing the chemicals. Don't smell too much, yes, but at least that's how we used to do it. I think you do that. So the way that we make a ester is actually from taking a carboxylic acid, such as say this guy here. Doesn't really matter. We'll just go with this guy. And we take a carboxylic acid and we react it with an alcohol like this guy. So if you have a carboxylic acid and you have an alcohol and you want to react them together, or if you don't want to react them together, you will make basically an ester, and esters are responsible for a lot of smells that we're familiar with. So, you know, that's why you'll be smelling some of the chemicals like pears and, you know, fruit type smells and wintergreen type of smell and those type of things. So they're responsible for a lot of smells, esters. Now, I would highly recommend that if you have a reaction such as this, that you take your alcohol and your carboxylic acid and actually turn them around, because it will make the reaction a lot easier for you to draw. What you want to actually happen is the hydrogen on the alcohol and the hydrogen on the carboxylic acid facing each other. So it'll make the reaction a lot easier. So what I'm going to do is I'm going to just, what am I going to do? I don't know. I'm going to erase that there, and I'm just going to draw it opposite of that and basically turn that guy around. So I'm just going to take this guy and redraw it the other way where the two hydrogens are facing each other. So we had HOH and it was 2 carbons, right? I believe. So the reason you want to do this is when we make an esterification reaction, essentially what's going to happen is we're going to remove water, is essentially what is going to happen. We're just going to take the water out, however you want to think about taking the water out, but you're going to basically grab out water, which is why it's sometimes easier just to get those hydrogens facing each other. Yeah. So the water is going to come out. And the reason I flipped it around like that is now I pretty much have my ester right there. All I'm going to do is just squish both sides together. So I'm going to take the water out and then bring everybody together. I'm going to start writing on this side and end on this side. So I'm going to do it underneath because I ran out of room, but I'm just going to write the product here underneath. So on the left, I have a CH3, I have a CH2, I have a carbon oxygen double bond. So that is this part right here. I obviously took this part in the box out to make water. I'm going to pick back up here with the oxygen, which is our ester connection, the carbon oxygen double bond to the oxygen. And I'm going to have my CH2 and my CH3. And now I have just made me an ester with the ester right there, basically. Yeah, that's the ester bond. It is basically made up of a carboxylic acid and an alcohol. Any questions on that? So you basically take out water, squish them together. And again, the easy way to visually see it when you have to draw it, get those hydrogens facing each other. And then you just put a box around water and then squish everybody together and you'll be golden. Again, you will have, actually in this case, you will have 100% of the molecule in front of you. If you take out the box and put those together, that's 100% of what you should make on the other side. You don't even have to add anything else to it. You basically just squish it together. Any questions on that there? So if we did another one, just to look at it here, we'll do so I'll let you, why don't you do this one here? Let's do, I'll turn the alcohol for you. All right. Why don't you draw the product of this guy here? Make sure that you end up facing each other because again, really all you need to do is box out the water. So that obviously is our water. And once again, now all we're going to do is just put them together. So again, I'll draw it underneath since I ran out of room there. CH3, CH2, CH2, carbon, oxygen double bond. I did nothing but copy what's in front of me. I'm going to skip the box and conclude over here. This will give me my ester connection, and I am done at that point. And I have my ester, obviously my ester bond in this region right there. Any questions on that reaction? So not too bad. I just got to remember, take water out, squish them together, basically. Yeah. So how do we name these? They're actually named based off of really the two things that make them up. They're named off the carboxylic acid and also the alcohol. So when we put these guys together, really the connection that you want to think about is right here, right? Now, if I go towards the single bonded oxygen, right? This is the alcohol part, right? And if I go towards the double bonded oxygen, that is our carboxylic acid part, right? So the alcohol part is always named as a group. So just like we would name a group, the group is the carbon group, and that carbon group is one carbon, which means it is a what group? It is a methyl group. The carboxylic acid part is named like the longest carbon chain that's there. And then you take out the last part of it and you put OH at the end of it. So this is one carbon, two carbons, three carbons, and four carbons. Four carbons is based off of butane. Drop the E and put the OH. So this is known as methyl butanoate. Yeah, and that would be the name there. So the first part of the name always comes from the alcohol part. And the way you can recognize the alcohol part is always start between the carbon and the oxygen and go away from, whichever way it is, depending on how it's drawn, away from the carbon-oxygen double bond towards the single bonded oxygen. And whatever carbons are there would be the group part of the name. And then go the other way towards the carbon-oxygen double bond, and that would get the O8 at the end of it. Question on that one. So we drew one on the other one. Let's take a look at this one. We would do the same thing here. We would look right here between the carbon and the oxygen. Going towards the single bonded oxygen is our alcohol part. And that is the guy that gets named as a group. So this has how many carbons? Two. Two carbons is a ethyl group, right? Going the opposite way towards the carbon-oxygen double bond is our carboxylic acid. It's got 1, 2, 3, which is based off of propane, and that's the guy that gets the O8 at the end of it. So this would be ethyl propanoate. No numbers, no nothing. That's basically the deal there, yeah. So the carboxylic acid basically gets the O8, and the alcohol part is named as a group. Question on that there. Now, let's say we wanted to draw one of these things and we're given the name. How would we go about doing that? Let's take a look at one of those together here. Let's say randomly we had, I don't know, we'll go with, how about pentyl? No. Let's go with pentyl ethanoate. Why not? Sounds like a fun one. All right, so that's pentyl ethanoate. So the first thing you're going to recognize is I got like an O8, so that should tell you it is an ester. Yeah. And again, what we want to think about is the functional group for an ester. And the functional group for an ester is really the carbon-oxygen double bond into an oxygen that goes into a carbon, right? So what we want to do is really, in this case, start with the functional group. So I would lay up the functional group in the middle. And now work my way backwards. So first off, I know the O8 part of the name is the carboxylic acid part, right? So that's ethanoate. So that ethane means there are two carbons. And the carboxylic acid part is the single bonded oxygen or the double bonded oxygen? It is the double bonded oxygen. Now, the important part though is I already have a carbon here, right? So I just need to add one more to give me two carbons going that way, right? So that takes care of this. Pentyl is the alcohol part, which should be coming towards the single bonded oxygen. And pentyl is how many carbons? 5. So I'm going to put 5 carbons. Now what's left is hydrogen. So we're going to lay up some hydrogens here. And hydrogen there. And there we go. Now we have our guy there. And again, our ester bond, right in here. Yeah, basically. So it's important to understand for an ester that the two components of it, and visually from the functional group, again, carbon-oxygen double bond is the carboxylic acid part, to the single bonded oxygen is the alcohol part. So when you need to put it back together, that is how you would do it. So we want to try one more here and then we'll call it a day. Let's just do, propyl. Butanoate. I hope that's not what it's on the other page. Okay. Well, we things is a good place to start is actually the functional group part. So that's what I'm going to just kind of put in the middle. And now I have the butanoate, which I know does come from the carboxylic acid. So that's going to head away from our carbon-oxygen double bond. The butane part of it means 4 carbons. Once again, we already have a carbon, so we just need to add 3 more to get us our 4 carbons that we need. And now to the alcohol side, which is where the propyl group comes. Propyl is 3, so we would add 3 carbons to this side, and that will take care of that. And now we're just going to put our hydrogens in to get to 4. And now we have our ester. This comes from obviously 1, 2, 3, 4 carbons for the carboxylic acid. 4 carbons is butanoic acid that comboed with a 3 carbon alcohol, which would be probably propanol. And because the O is on the first carbon there, probably 1 propanol. So those are the 2 things that basically put this guy together to make our. What's that? No, I don't know, but no. So let me just do this real quick. If you drew it like what I'm going to draw right now, the answer would be no. If you did this, yeah. So if you drew it like this, and you did this, then it's right. So if you put only like 3 carbon, I'll put an X here. If you did just 3 carbons there, I'm putting my hand over my screen, but you're not seeing it up there, are you? That's I guess I can actually do it up here. So if you just put the 3 carbons coming this way and the 4 carbons going that way, it would be incorrect, because the single bonded oxygen is for the alcohol, and in this case the alcohol was only propyl, I think, or propyl, so it should only have the 3 carbons on that side. So that's why kind of the single bonded oxygen in this case and the double bonded oxygen are important. Anything that kind of is attached to the double bonded oxygen should come from the carboxylic acid. So that part of the name is where those carbons should be. And anything attached directly to the single bonded oxygen would come from the alcohol, and that's where those guys should be. Other questions? Okay, thanks for hanging out.